in this lesson, we're coming back and looking at the applications of logarithms. So recall we have two formulas that we've been using. One is for compounding interest rate, a equals p naught 1 plus r over n to the nt, and one is for growth and decay, a equals p naught r to the little t over big T. And the formatting isn't very good here. Let me just write it again. P naught r to the power of little t over big T. So our exponent is that fraction, where we remember that this capital T refers to the length that it takes for r to happen. Capital T is the length of the r life. Little t is the time that we left the sample. We're going to look in class at one that gives us continuous growth and decay. So I'm going to go through some examples right now, and we'll explain this more fully when you get to class. So if the growth and decay is continuous, we use the formula A equals P naught e to the KT, your pocket formula. So A, once again, just like the other cases, is the final amount. P naught is the initial amount. T refers to time. Two things are different. E, the base for this equation is E. It is an irrational number similar to pi, 2.7182 infinitely expanding decimal. K is your proportional constant. It's like your R value. So let's do a few examples. I think you'll get the idea, and I'll explain where the E comes from and why we do this kind of a calculation in class on Monday. So let's look at estimating the time required for $5,000 to grow to $30,000 if it's invested at 10% compounded monthly, compounded continuously. Okay, compounding. So when we're using a compounding interest rate formula, then in all of our questions, we start by letting our reader know what formula we're using. A is equal to P naught 1 plus R over N to the power of N times T. And we set up a key, so anybody looking at our work can follow along with what we're doing. Okay, so let's have a read through the question, highlight the important information, and identify it. Estimate the time required. Okay, so that's telling me that I don't know what time it is. And required for 5,000 to grow to 30,000. So it starts at 5,000, it ends up at 30,000. This is P naught, and this is the final amount. It's invested at 10%, meaning my R value is 0.10, and it is compounded monthly, telling me that 12 times a year I get that interest payment. So my final amount, 30,000, is going to equal my initial amount, 5,000, bracket 1 plus R over N to the power of N times T. And T is what I don't know. So I have an equation where the variable is in the exponent. Whenever you need to solve for a variable in an exponent, you need a log. So before we take this from exponent form to a log form, we isolate the exponential. And it's really important that the very first thing you do is divide both sides by 5,000. So 30,000 divided by 5,000 simplifies this equation to 6 equals 1 plus 0.10 over 12 to the power of 12t. So to solve for a variable in an exponent, we need a log. We're going to take the log of both sides. So the log of 6 will equal the log of 1 plus 0.10 over 12 to the power of 12t. log laws tell me that this power can come down in front as a multiplier. So your power law for logs tells you that this can be simplified to 12t times the log of 1 plus 0.10 over 12. Our goal here is to solve for t. Let's divide both sides by the log, divide both sides by 12, and I get the log of 6 divided by 12 times the log of 1 plus 0.10 over 12 will equal t. So you can put this in your calculator. Be careful that you put brackets in your denominator. Go ahead and try that now. Make sure that you're getting this for the answer. If you're not, let me know, because you're having trouble with calculator entry, and we need to clarify that. Okay, so times 17.99 years. I guess we could round that off to 18. Okay, if it's growing continuously, and like I said, we'll discuss what we mean by this in class on Monday, so part A, part B. If it's continuous growth, then we're using this formula. A is equal to P naught E to the KT. And once again, we're going to set up a key. Notice I'm not putting E in there. E is a constant. It is always 2.71821, etc. A, our final amount, same thing, 30,000. Still starting with $5,000. And our K, our constant of proportionality, is 0.10. And once again, we're trying to find time. So we have 30,000 is equal to 5,000 e to the 0.10 t. So an exponential equation with a variable in the exponent. We're going to start off by dividing both sides by 5,000, and I get 6 equals e to the 0.10 t. And here we're going to do a little aside. So I want to take the log of both sides. When the base is e, then I want you not to take the log of both sides, but I want you to take the ln of both sides. So the ln of a number is the same as log to the base e of that number. So the base of e is called the natural base for the logarithmic function. It comes up so often in the natural sciences that we give it a special name, ln. And as I said earlier, you have two ways to calculate a log on your calculator, a base of 10, and this one is the base of e. So if you wanted the log of 10, if you want the ln of 10, you're calculating it to a different base. So this is saying, to what power do I raise e in order to get 10? I raise it to this power. Let's check. If you take e, and there's the number e right there, on your second divide, and raise it to that power, what do you get? 10. Okay, so we're going to be using a ln function, which is a log function. So we've got 6 is equal to e to the 0.10 t, and doing the same thing to both sides of the equation, taking the ln. And because a ln is a log, the rules work exactly the same. That is, we've got ln 6 equals 0.10 t times the ln of e. Okay, here's why this is handy. Guess what the ln of e is? Well, it's asking you, if ln is log to the base e, it's asking you to what power do you raise e in order to get e? 1. So the ln of e here is just 1. So this becomes ln 6 is equal to 0.10 t, and ln 6 over 0.10 equals t. So plug that in your calculator. Ln 6, close the brackets, divided by 0.1, and I get 17.91759,469, and let's just round that off to 17.92. years. Okay, so if we compound our interest continuously, it takes a little less time for us to get to $30,000. Okay, over the page, let's look at a half-life problem.